Hello everyone! In the previous video, we looked at what you need to know about AD converters in general. Now, we're going to take it a bit further and see how the analog-to-digital converter on the STM32F446 microcontroller works.
Three 12-bit successive approximation ADCs are integrated into this microcontroller, each with 16 external channels.
This means that an ADC peripheral can process up to 16 different analog signals on different inputs. We won't explain how a successive approximation ADC works in this video, but if you are interested in the working principle, you can read about it in the written curriculum.
Looking at the full measurement range, we can say that it can perform conversions from 0 volt up to a reference voltage. This voltage must be connected to the dedicated VRF leg of the microcontroller. The requirement for this voltage level is that it must be at least 1.8 volts and at most equal to the supply voltage. However, the ADC can also be used with an internal reference voltage equal to the microcontroller supply voltage, 3.3 volts for the development board. Using an external reference voltage can narrow the measurement range, thus increasing the conversion sensitivity and allowing to distinguish smaller voltage differences. This, however, means that the measurement will be more sensitive to surrounding noise, which is not necessarily beneficial. An additional benefit of the external reference voltage supply is that it allows a more stable and accurate voltage source to be connected using a separate precision power supply.
In the case of our microcontroller's ADC, there are 4 conversion modes to choose from: single, continuous, scan, and discontinuous.
The single conversion mode is the simplest, as the conversion is done to the current analog value and then the process stops. This mode should be used when you want to perform a conversion at a dedicated time during the running of the software. In continuous conversion mode, when the conversion is finished, the next one starts, that is, the conversion is continuous. This mode can be used, for example, when you want to measure the value of a temperature sensor continuously. Scan mode is essentially a single or continuous conversion, but to multiple channels rather than one. The conversion ends after the last conversion. This mode is useful when, for example, you want to measure the output of several sensors continuously. Finally, discontinuous mode means that the conversion will only start when an interrupt occurs, such as the expiry of a counter. This mode is an obvious choice if, for example, you want to measure the battery voltage of a device at certain intervals.
The conversion time is made up of several parameters. It depends on the chosen bit width, the clock frequency of the ADC used, which in our case is up to 42 MHz, and the sampling time. Danny is about to show you a sample rate calculation.
For example, suppose we want to digitalize our signal at 12 bits with the minimum sampling period of 3 ADC clock cycles specified in the datasheet. This will be done in 15 ADC clock cycles, since we measure the signal for 3 clock cycles and then take 12 clock cycles to adjust the result bits one by one. If we divide the maximum ADC clock frequency of 42 MHz by 15, we get that the ADC performs 2.8 times 10 to the 6th conversions per second, that is 2.8 megasamples per second, or MSPS. The sampling rate is usually given in samples per second, which is abbreviated as SPS. The mega prefix refers to the order of millions.
Let's look at the possibilities for reading the result of the transformation. There are 3 different ways to do this. The first of these is the polling, the second is the interrupt, and the third one is a direct memory access, or DMA for short.
Let's go through these in a bit more detail. The simplest is the polling mode, which means that once the conversion is started, we wait for the result until it is ready for us. This keeps our microcontroller busy while we wait. It will not perform any other calculations during this time. We can also use our ADC peripheral in interrupt mode. In this case, an interrupt is generated in the microcontroller when the conversion is complete, and then the corresponding short function, called a callback function, is run. The function is executed when our program is interrupted. In this case, our microcontroller is not busy during the conversion. It can even perform other operations while the conversion is running in the background. A third way to read the digitalized result is the DMA mode. This saves a lot of processor time, as a separate unit will handle and store the conversion results with direct memory access, taking the load off the processor, and the processing will be done in a part of the program that we define. The ADC in the microcontroller has one more feature that can be very useful in many cases, and that is an analog watchdog.
Exactly, it is a very useful element of the ADC. Sometimes a signal may only be suitable for us within a certain voltage range, for example for a temperature sensor. If this signal goes out of range, we want to be notified immediately. This is where the analog watchdog can help, comparing all values to the limits like a window comparator. We need to specify the lower and upper limits of the range, and then if the measured value is outside the range we have specified, we will be notified. The monitoring is done in the background, so we do not have to monitor the event in software, making our job easier.
We will see how easy it is to manage the ADC with the library provided by ST, as it hides the register management from us. This makes it quicker and easier for us to use the peripheral, and thus helps us in our development and the portability of our software between different types of STM32 microcontrollers. Before we get to the use of the library, it's worthwhile to have a broad overview of the main registers associated with the STM32 ADC peripherals, which will help us to understand the process in more detail. The first, and one of the most important registers for us, is the ADC_SR register, that is, the status register. From here, we can get a lot of important information about the current state of our peripheral, such as whether the conversion has started or finished, and also the watchdog event is stored here. There are two control registers called ADC_CR1 and ADC_CR2. These registers contain the configuration of the peripheral, which is specified during initialization and can be modified during the running of the software according to your needs, such as how many bits of width, what sampling rate, and what mode we want to use the ADC. It is also possible here to enable different interrupts. In the ADC_SMPR1 and ADC_SMPR2 registers, you can specify how many clock cycles to sample from the signal during a conversion. Of course, sampling over more ADC clock cycles may give more accurate results, but naturally, it will take longer. The previously mentioned analog watchdog limits, that is, when to signal, can be set with the ADC_HTR and ADC_LTR registers. The former will store the upper limit, while the latter will store the lower limit. The last register left is the ADC_DR, where the result of the conversion is written. This is where we will extract the binary representation of the analog signal.
Now that we have a good amount of theoretical knowledge, in the upcoming video we will do nothing less than show you 3 example programs running on the STM32 microcontroller on your desktop. So, if you have a Nucleo development board, be sure to look for it, as you will need it during the next video. Stay tuned.
See you!
Bye.